So what is it that makes PortSaver special? Why do we need it? Where do these transients come from? What kind of damage can it do? Picotest uses their own equipment, and we designed PortSaver really because it was important to us. Very often we connect higher voltages to an oscilloscope that it can tolerate. Maybe we want to see very low noise on a 48 volt bus or a 60 volt bus. And one way to effectively do that is to put a DC block in front of the oscilloscope. And what that'll do is remove the DC part of the measurement so that we can use very small division settings to get very sensitive settings so that we can measure very low levels of noise. And that works pretty well. But there are a few things that get in the way. The first is when we first connect this DC block to the 48 volt or 60 volt power supply, the capacitors inside it aren't charged. And so those charge through the oscilloscope, generating a very large inrush, which can easily damage the front end of the scope from excessive voltage or current. And adding to the complexity of that, the specifications for the front end are not all that clear and not all very well detailed. And I don't want to blame anybody, but for sure, sometimes engineers do stupid things, myself included. And we'll connect these DC blocks thinking, oh, this is fine, it's going to take out the DC part. And personally, I have wiped out the front ends of 2 oscilloscopes, which are very delicate. How much did it cost to replace them? I needed to replace just the front end, which is the front board in this panel, and that includes the 8-channel interface, essentially. And that cost anywhere between about $5,000 and $10,000 per instrument to fix. So it's a very expensive repair, and you try not to make that mistake more than once, but it is relatively easy to do it. There are other problems with DC blocks also, and that is that most of them are made for RF applications using ceramic capacitors. And that leads to 3 different problems. One of those problems is that being a high frequency device and being ceramic, they don't care too much about the capacitor. In low frequency measurements, we do, because that capacitance changes as we apply DC voltage or AC voltage to it, making it very difficult, not impossible, to calibrate, particularly with vector network analyzers. Also, we could actually connect one of these DC blocks and we could connect it to our 60 volt power supply, and we turn everything off and we forget about it. We take the DC block and connect it back to the oscilloscope, and we forget the fact that it was left there with a charge of 60 volts, and poof, again, we wipe out the oscilloscope. So there are a lot of things that are special about PortSaver. One is that it doesn't use ceramic capacitors. It uses a bipolar arrangement of tantalum. And in that way, we eliminate the piezoelectric noise, we eliminate the DC bias effects, and we eliminate the AC bias effects. That makes it easier to calibrate, makes our measurements more accurate, and it also makes it so that we can get to much lower frequencies. So there's a lot of benefits to that. There are a few other things. We make different models of it. There's a P2131 and a P2132. And that allows us to optimize it for particular frequencies. It allows us to put in inrush limiting. All of these have self-charge and self-discharge, and they also include transient suppressors. And the transient suppressors are designed to squash or clamp any signals that could be damaging to the oscilloscope before they get to the oscilloscope. Like I said, engineers sometimes do stupid things, and this is actually what happened to one of our PortSavers when somebody connected it to something that it should not have been connected to. And the interesting thing about this is that as damaged as this PortSaver is, the scope survived, and there wasn't any residual damage to it. It didn't require recalibration. There was no damage at all to the oscilloscope. So the PortSaver, I guess you could say, sacrificed itself for the greater good. Let me just show you how that works. The P2132 was specifically designed for sensitive spectrum analyzers. It's designed to go to very low frequencies, about 2 hertz. And because of that very low frequency operation, the inrush current would last a lot longer than it would in a higher voltage device. And the spectrum analyzers are very sensitive with very poor specifications about the damage limits. In this particular case, we had a customer that wanted to protect their N9020 spectrum analyzer, and they believed that the limit was about 200 millivolts peak. They asked us if we could make a DC block for that, and we did. So here, I'm putting a 1 megahertz signal through the DC block. It shows up as an AC biased signal, whether I have DC offset or not. And if I were to make this signal larger, you can see that eventually we do clamp the internal protection diodes, and you can see that those did clamp well below the 200 millivolts, protecting the $300,000 spectrum analyzer. And so port savers are kind of a very inexpensive insurance policy, but also it's a better DC block that has self-charge, self-discharge. It doesn't have calibration offset issues that you would have with ceramic isolators, and it can go to much lower frequencies.